Hello and welcome to this talk. My name is Richard Spence and the topic is on sparse and lightweight spanners in weighted graphs with local additive error. So what is a spanner? So we're given a graph G. We say that a spanner is a subgraph H which approximates the distances in G up to some amounts of error. So a bit more formally, given the graph G and some distortion function f, we say that H is a spanner of G if the following spanner inequality holds for every vertex pair U and V. So the below lists some of the applications of spanners in graphs, typically when we want to compress the input graph, but not lose too much information about distances. So here are two common types of spanners, multiplicative and additive, based on the amount of distortion allowed. We'll mainly be focusing on additive in this paper. So a brief history about spanners. Multiplicative spanners were the first type of spanner introduced in the late 1980s by Peleg and Schaefer. And then a few years later, the following seminal results was proven that said that for all integers t greater than or equal to 1, every weighted graph G has a 2t minus 1 spanner with size roughly n to the 1 plus 1 over t, which turns out to be optimal assuming a girth conjecture by Erdős. And then additive spanners were introduced in the late 90s, and there's been a wide field of research involving both of these types of spanners. So as mentioned before, we focus mainly on additive spanners in this paper. One advantage of additive spanners is that the error does not scale with the distance in general. So more formally, given a graph G and some positive number beta, we say that a plus beta spanner has distortion x plus beta, meaning that distances in H are no longer than beta units away from distances in G. So on the graph on the left, we have the graph G, and on the right, we have a plus 2 spanner H, and we can see that every pair of vertices, the distance in H is not more than 2 edges longer than the distance in G. A few additional types of spanners based on the set of vertex pairs for which distances must be preserved, as opposed to the distortion function. So generally, we say that an all-pair spanner, or just a spanner, preserves distances between every pair of vertices, but we may only require that distances are preserved between specific pairs of vertices. So we call these pairwise spanners. And a subset-wise spanner is a special case of the pairwise spanner, where the vertex pairs are of the form S cross S for some vertex subset S. So the following table contains known results about the upper bounds of the size of different spanners in unweighted graphs. So for example, the way to read this chart says that every graph has a plus 2 spanner on roughly n to the 3/2 edges. And this is consistent with the idea that if we increase the additive error beta, we expect to get sparser and sparser spanners. Same with the pairwise case, where increasing beta should lead to sparser and sparser spanners asymptotically. So all of these results are in unweighted graphs, but what if G happens to be edge-weighted? So in this case, we have to be a bit careful with how we define the notion of additive error. So one immediate way we can define additive error is to assume a constant error. However, this is not really interesting since we can always scale the edge weights large enough such that the graph has no non-trivial spanner. So a more natural way to define error is in terms of the maximum edge weight. And so this was the concept of our previous paper last year involving spanners that have global error, where the additive error is in terms of the maximum edge weight in the graph. However, a slightly better type of error is to consider local error, where the additive error between any vertex pair is in terms of the max edge weight along its shortest UV path. pi uv. And so local error is more desirable in settings such as the below, where we may have a shortest path where the max edge weight is much less than the max edge weight in the entire graph. So the following table lists known results involving weighted versus unweighted additive spanners. So the first two rows are the same as before. So the main takeaway is that all of the size bounds from the unweighted case do hold for the weighted case, with some additional dependence on epsilons, which arise for a technical reason, which we'll get to in a bit. And the results in green are the ones that we show in this paper. So the main algorithmic ideas behind these spanner algorithms in weighted graphs all rely on a initialization, and then most of them rely on a spanner completion technique. So the first phase is what we call D-light initialization. So in this phase, we simply add a certain number of edges incident to every vertex. So we add D lightest edges incident to each vertex, where D is some parameter to be chosen. And then for pairwise spanners, we're also going to additionally add a certain number of edges along each pair's shortest path. So note that this first phase does not care about distances in the spanner. This is mainly just to initialize the spanner so that we can perform the second phase and analyze the size bounds. So for the second phase, we call this plus beta spanner completion. So we iterate over each vertex pair in order of increasing maximum weight. And then we'll ask, is this vertex pair currently satisfied? Meaning, does the spanner inequality hold for that vertex pair? If not, then we'll add the shortest path to the spanner. So it's easy to see that after the second phase of this generic construction, we have a valid plus beta spanner, since we will have iterated over each possible vertex pair. So the question is, can we analyze the edge bounds? So here's a more concrete example. So one of the results is that we show that every weighted graph has a pairwise +6 plus epsilon W spanner on roughly n times p to the 1/4 edges, where p is the number of pairs. So the construction is to take a D-light initialization, where D is chosen to be the number of pairs to the 1/4. And then for each vertex pair in the input, we'll add the first and last L edges along that pair's shortest path to the spanner, again with L being carefully chosen. Lastly, we'll perform a +6 plus epsilon W spanner completion. So you can easily see that both steps 1 and 2 are going to add roughly n times the number of pairs to the 1/4 edges. So what about this spanner completion? So in order to determine the size bounds, we're going to need the following neighborhood lemma from Ahmed et al. Last year, which says that if H is a D-light initialization, and we look at a shortest path pi uv, and look at the number of edges that are contained in the path but missing from the D-light initialization. So suppose there are L edges in the path which are absent from this initialization graph. Then this neighborhood lemma states that there are at least D times L, or omega D times L vertices in the graph, which are adjacent in the initialization to some vertex along the shortest path. So this image below kind of gives a graphic representation of what this neighborhood lemma looks like. Note that the vertices in the neighborhood may be contained on the path, but not necessarily. So this lemma is pretty easy to show in unweighted graphs by a direct counting argument, since you can show that no vertex can appear adjacent to more than 3 vertices along the path, Otherwise, that would contradict that we have a shortest path. So this lemma is pretty easy to show in unweighted graphs, but trickier to show in weighted graphs. So we're going to apply this lemma in order to consider when we add a shortest path pi uv to the spanner during the spanner completion. We're going to use this neighborhood lemma to ask the question, how many pairs of nearby vertices are there whose distances sufficiently improve when I add the shortest path to the spanner? So we'll let uv be a pair such that the path pi uv is added during the spanner completion. And we'll suppose that z edges are added where z is at least 1. And we'll look at the subpaths containing the first L edges, the last L edges, and the intermediate path that contains the edges that were added. So remember that after the initialization, we added the first L edges and the last L edges to the path, if not already. So using the previous neighborhood lemma, we can establish a lower bound on the number of choices we have for the vertices A, B, and X, where A and B are necessarily neighbors of a vertex along the first and last L edges, and X is a neighbor of the subpath containing the Z edges that were added. And so it's not too difficult to show that when we add the path pi uv, then this is going to improve the distance between either the pair AX or the pair XB sufficiently. By sufficiently, we mean by at least an order of epsilon WUV. So note that this is where the epsilon comes in because in unweighted graphs, any sort of improvement in the distance must be by at least 1. But for weighted graphs, the distance between a particular pair may only improve slightly. So we have to consider the number of vertex pairs whose distances sufficiently improve. So this idea was also used by Elkin et al., who showed that every weighted graph has an all pairs +6 plus epsilon W spanner and a subset-wise +2 plus epsilon W spanner with edge bounds the same as the unweighted case. So by considering the total number of possible improvements over all possible paths that we add during the spanner completion, we can set up an equation in terms of the number of edges that were added during spanner completion. Suppose it's uppercase Z, and then we can solve for the number of edges added during the spanner completion. And so note that we've chosen D and L in order to balance the number of edges added during both the initialization phase and the spanner completion phase. So using this similar idea, we can also prove a pairwise +2 plus epsilon W spanner with roughly n times the number of pairs to the 1/3 edges. So all of these previous results involving weighted additive spanners, all of these consider the size or the number of edges. But what if we want to minimize the total weight as opposed to the size? And so this is a fairly natural question, since a good analogy may be if I want to construct a road network, I want my roads to roughly preserve distances between individual towns. And a natural question is to minimize the total length of the road network and not care too much about the number of roads. So this is where this notion of lightness comes in. So we typically define the lightness of a subgraph in terms of the MST, since the minimum spanning tree is the cheapest possible way to connect all the nodes. So that's where this definition of lightness comes in. The ratio of the total weight of the subgraph divided by the weight of the MST. So the notion of lightweight spanners is fairly well studied in the multiplicative setting, but not nearly as much in the additive setting. So the following table contains the second set of results in this paper that state that every weighted graph has a plus epsilon W spanner with roughly O of n lightness up to some epsilon term. That's about the best that you can possibly do. We also show that every weighted graph has a plus 4 plus epsilon W spanner with roughly n to the 2/3 lightness, and this lightness bound could possibly be improved. So note that the left two columns contain the lightness results for unweighted graphs. Note that lightness does not really make a whole lot of sense since the minimum spanning tree always has weight n for an unweighted graph. So the notion of lightness is not too interesting in unweighted graphs, but it serves as a good comparison. So we remark that these lightness results do not depend on the maximum weights or the edge weights of the graph, just the size of the graph. So the main algorithmic idea in these lightweight spanners is we're going to modify this initialization process. So instead of adding a certain number of edges for each vertex, we're going to add edges with a total weight at most d for each vertex. So the d lightweight initialization is we're going to start with the minimum spanning tree. And this adds 1 lightness, so we don't really pay much. And then for each vertex, we're going to add edges incident to that vertex in non-decreasing order of weight until the next edge causes at least d weight to be added corresponding to that vertex. So for each vertex, we're going to add edges of total weight at most d. And this will be the completion of the initialization step. And then the second phase of the lightweight spanner algorithm is we're going to do a spanner completion as before, where we iterate over each vertex pair and ask, is the spanner inequality satisfied for that pair? If not, then we'll add the shortest path to the spanner. So the analysis is largely the same, except we're going to need one additional step. So in order to analyze the lightness, we're going to consider the number of improvements when we add a shortest path to the spanner. But we're going to consider the number of improvements in a subdivided graph. So we define this subdivided graph as follows. So the first step is more of a convenient step. We'll assume that the MST has weights, say n or n over 2, just by scaling the edges linearly. Note that this does change the max edge weight, but whether a graph is a valid spanner does not depend on how we scale the edge weights. So we can assume without loss of generality that the minimum spanning tree has weights, say n over 2. The second step is more important. So we're going to subdivide heavy MST edges. So specifically for each MST edge of weights greater than 1, we're going to subdivide that edge into a bunch of smaller edges of weight less than 1. So more specifically, we're going to subdivide each edge E into this many edges of weight, the weight of the edge divided by the ceiling, which is at most 1. So note that this is not going to change the weight of the MST. So on the left, we have a graph with the minimum spanning tree shown in bold. And then we can basically scale the edges for free by dividing by 10. And then once we do that, we're going to have an MST edge of weight 1.8, specifically this diagonal edge. And we're going to subdivide that into 2 edges of weight 0.9. So that will be our subdivided graph G prime. So the following gives the lightweight analog of the neighborhood lemma that we saw for the sparse spanner case. So this lemma states that if H is a D lightweight initialization, again, we're going to look at a shortest path pi uv in the original graph. And then we're going to look at the total weight of the edges that are absent in H along the shortest path. Note that in the previous neighborhood lemma, we were looking at the number of edges, but now we're looking at the total weight. So this lemma states that there are basically omega of z vertices in the subdivided graph G prime, which are at most a given distance WUV from some vertex along the shortest path. So note that the corresponding lower bound for the neighborhood was d times L in the previous neighborhood lemma. So note that this, the bound of epsilon prime z does not depend on d, just the total weight of the edges. So the main ideas behind determining lightness of the resulting spanners are essentially the same as before, except that we're going to consider the subdivided graph and ask, when we add the shortest path pi uv, how many vertex pairs in the subdivided graph are there whose distances improve sufficiently? And by sufficiently, we mean by, as before, on the order of, say, epsilon times w uv. And once we answer this question, then we can choose the parameter d in order to balance the total weight added during both the initialization and the spanner completion. So it turns out for the plus epsilon w spanner, we can just set d equals 0, which is the same as initializing with the minimum spanning tree. For the plus 4 plus epsilon w spanner, we'll set d to be n to the 2/3. So several open problems in future directions in the direction of weighted additive spanners. So the first open problem, which we have mentioned before, is can we improve the lightness bound for the plus 4 plus epsilon w spanner? And the second question is, can we consider similar types of additive spanners, say plus 2w plus 6w, or perhaps plus w times some weak polynomial in n, additive error. So in this case, we would expect to obtain sparser spanners, but with the price of more additive error as before. Since in general, when we increase the amount of error, our spanners should be more and more tree-like or more sparse. Lastly, can we construct additive spanners in weighted graphs that have both a non-trivial size and a lightness bound? So note that each of the spanners in this paper have either a size or lightness bound, but not both. So with that said, I'd like to thank you for your attention, and I'm happy to take questions during the short talk portion of this conference. Thank you.